My window is, oh, here we are. Oh, yeah, this looks good. Thank you.
Okay, perfect. Sounds good.
Great. Thanks.
Good. I'm glad we sorted that beforehand. Okay, so we're still looking for note takers. Yes, thank you. So just, you don't have to record anything that's in the slides. You just have to record the discussion mostly. Because, questions and discussion is mostly what they want.
Deb, who was that who volunteered to take notes?
I mean, anything you do is better than. So there's a hedge doc document you can see in the, right? You got it? Cool.
So could you identify yourself who volunteered to take notes?
What's your name? Ben? He's having trouble signing in.
Could we have a backup note taker as well?
Anybody, so it would be nice if other people would give him a hand with the note taking. That'd be awesome, Leaf. Thank you. All right, I think you're square note taker wise.
Okay, perfect. Sounds great. I think we can begin. Hey all, welcome to KEYTRANS, and happy end of IETF week. I am one of your co-chairs, Siobhan. Prachi couldn't make it, she's on PTO, but she sends her regards, and I am joining remotely, obviously, and thanks, Deb, for helping us share. Let me actually also share my note well. You've seen this at several points this week, I'm sure by now, but please do note it extremely well. It covers your participation at the IETF, both on-site and remote, and covers various topics such as patents and code of conduct. Yeah, please do go through it and familiarize yourself. Just some meeting tips, the most important being that please do use Meet Echo for joining the queue so that we can be fair towards remote folks, and also just makes it a lot easier to manage the queue if you're using it. And note that if you're not using the on-site Meet Echo tool, then to please record your participation using the Blue Sheets QR code that should be up somewhere in the room. And yeah, the agenda is up here. I'll give a quick update. And basically, we have one adopted draft, the architecture document that's been worked on for a while. Thanks to Brendan for that and everyone who has helped him. At the last meeting, we discussed how we need a protocol document to think about the architecture document concretely. Brendan and Felix have an early draft up now, and which got some discussion on the mailing list. And so the agenda for today is to discuss the new protocol draft. And we can keep the bulk of the time to discuss that. And Isha will also be giving a presentation on contract monitoring and auditing modes in relation to the protocol draft. And yeah, the overarching goal is to make progress on the protocol draft and see if folks think we're headed on the right track for eventual adoption. Does anyone have opposition to that? Going once, going twice? Then if not, we can begin. Brendan, can you come up for the protocol draft discussion?
So I think, are you going to run the slides for him, or do you want me to?
Oh, Brendan, will you be sending slides, or should I run them for you?
Whatever you want.
Either you run it or he does?
Yeah, he can. Well, he's running. He's opening
Okay.
it.
That sounds good.
The trick is you'll have to say next slide this way because I think the clicker won't work.
Oh, yeah. Okay, that's fine.
Okay.
But yeah, I'm here today to present a draft that I wrote with Felix Linker, and it's the protocol draft for key transparency. And just to like frame the conversation a little bit, I'm sure that we will get into the conversation about like, is this actually the draft that we want to adopt or not in the end? But that conversation is a lot less important to me than actually making sure that people are able to understand the draft, because I've talked to a lot of people who are like, key transparency seems super cool. I'm really excited about key transparency, but the papers and the drafts and stuff that I read make no sense to me. So if we're able to make sure that people understand the draft, that would be a very, very good outcome for me. So, I mean, more than usual even, please feel free to come up and ask clarifying questions. Next slide. So just to remind people of the basic model of what we're building, we are building a protocol between a client and a server, which is basically a key value database. So there are 3 different things that users will want to do with the server. The first thing is to search for the value of a key. They could also want to update the value of a key and also want to monitor. And monitoring is essentially saying, you know, I already know what the values of these keys are. I just want to make sure that they haven't changed since, you know, last I checked in. And what's important is that I want cryptographic guarantees under all of these operations so that I have a really high degree of certainty that I'm not being lied to. You know, like if I search for a key and I get a value back, I want to be very, very sure that if anybody else searched for the key, they would get that same value back. So that's what we're looking for as we're building. Quick
Brendan,
note.
could you, sorry, just a quick note. Could you move a little bit closer to the mic, just so that's a little bit clear?
Be louder. He just needs to be louder.
Okay, so I was going to say one quick note on terminology. I'm going to say the word key a lot in this presentation. Every single time, I will mean a lookup key in a key value database. I'm never going to say key and mean a cryptographic key. There are no cryptographic keys in this presentation whatsoever, just so we're clear. That's been a huge point of confusion. Okay, next slide. So to get into the tree construction, next slide again. The tree that we're talking about is a hash tree. To kind of introduce hash trees generally, with a hash tree, you have some set of data that you're interested in, and you want to commit to it in a compact way. So what you do is you take all of your individual pieces of data and you hash them, and each of those hashed pieces of data are a leaf node, and they correspond to the leaf nodes of your tree. And then what you do is you compute the intermediate nodes, and each intermediate node is the hash of a few children node below it, and you kind of keep going up like that, sort of computing the hashes of lower nodes up and up until you get to having a single hash left, and that hash is what's called your root node. And so next slide. Hash trees are great because they let you commit to very, very large amounts of data in a very compact way. They're also great because they let you selectively reveal small subsets of that data. So in a hash tree, you have something called the copath. And the copath is the list of nodes that I can hash together with some specific leaf node to recompute the root. So if you look at this diagram, we have leaf node 001 as it's labeled here. The copath for 001 is all of these other nodes in gray. It's 000, which I can hash together with 001 to get node 00. And then I hash together that node with 01 to get node 0. And then I hash together node 0 with node 1 to get the root. So that's the copath. A lot of times in the more like protocol specific parts of the conversation, I'll say that we'll give a user, you know, some value, and that value is the leaf of a hash tree, kind of unspoken. We're giving the user that leaf value, but we're also giving the user the copath so they can actually verify that that leaf data is actually in the tree that we're saying it's in. So next slide. The first type of hash tree that we have in the draft is what's called the log tree, which is more specifically called a left balanced binary tree. And with the left balanced binary tree, the defining property is that every left subtree contains the largest power of 2 nodes that's possible. So if you look at the diagram on the left here, it's got 5 leaves. And so that first like left subtree in there contains 4 leaves because that's the largest power of 2 that's possible to put in that subtree. And then whatever is left kind of gets stuck in the right subtree. Log trees are really, really nice because it's easy to append new data to them. So we have the diagram going from 5 leaves to 6 leaves. When we add our 6th leaf, we add a single sort of intermediate parent node. And then we change where the root node sort of points to as its right child to that new intermediate node. And so that's how you add new data to a log tree. It's basically always constant time, or at least logarithmic. And this is harder to kind of talk about graphically, but also with log trees, it's really efficient to provide consistency proofs, which means if you have a log tree with 1 billion entries in it, and then you come back later and there are 2 billion entries in the log tree, it's really efficient for me to prove that the log tree with 2 billion entries in it actually has all of the same entries as the log tree with 1 billion entries in it, just with new stuff added. So I have a guarantee that none of the stuff that I showed you before was ever removed. And yeah, so the sort of abstraction here that you want to think about is this is a log. It's just a list of entries. And the tree structure on top is a way to commit to that list of entries efficiently. Next slide. Okay, the second type of hash tree that we have in the draft is called the prefix tree. Also kind of called the trie. It varies, but the defining property of the prefix tree is that every path from the root to a leaf node corresponds to the prefix of some string that's stored in the trie. So what we're committing to here is some set of strings. So if you look at the diagram, we've got the strings and, dad, do. We want to commit to those. And so what we do is we build that kind of tree structure on top where each branch in the tree corresponds to one character in the prefix of that string that we're interested in. And the reason this is nice is because it's really easy to provide proof that a specific string is or isn't in the tree. So if I want to show that, like, if I want to cryptographically prove that the string dad is in the tree, I can just kind of go down. I can give you the leaf node for dad, and then I can give you the copath for dad, and you can hash those together and get the root hash and check that that actually is in the tree where I said it was. And you can do kind of a similar thing for proofs of non-inclusion as well, where I can basically follow a path until it hits, you know, either a different leaf or like a child that doesn't exist, and that would be convincing to you that this actually does not exist in the tree. Next slide. Okay, so these two sort of basic hash trees are combined into what is cleverly called the combined tree. So the combined tree is at the top level a log tree, and then each leaf in this log contains 2 things. It contains 1, a cryptographic commitment, and 2, it contains the root hash of a prefix tree. So this sort of diagram here, each gray box is meant to be a leaf of a log tree, and you can see one comes after the other. They're sort of in order. And then you've got the little triangle, which is the prefix tree corresponding to each log entry. Next slide. So to put a little bit more color on what is actually stored in the combined tree, the cryptographic commitment is a commitment to a statement that some key value pair was inserted into the log. And then for the prefix tree contains the total set of key version pairs that have ever been inserted in the log. So if you start at this first log entry that's over here, the commitment is some commitment saying that Alice's key is now assigned to X. And then we insert in the prefix tree a pair of Alice and then 0, because 0 corresponding to this being the first version of Alice's key. Then we go to the next log entry, we say Bob's key is now Y. We add Bob 0 to the prefix tree to say this is the first version of Bob's key. Then we go to the next one, Alice's key is now Z, and we actually add a second entry saying Alice 1 to correspond to the second value of Alice's key. And we just kind of keep going like this forever. Next slide. So given that that's how the tree is built, the next question is how do we actually search the tree and make it useful? Next slide. So if we kind of step back and think about what does the combined tree represent, It's basically a write-ahead log in a database where each entry in the log is saying the database was changed in some way. And normally, a write-ahead log is not super useful because you would have to read the entire write-ahead log to compute the current state of the database. But in this case, we also have the prefix tree. And in the prefix tree, we can look in there and see what the greatest version of a key that exists at that specific point in the log was. So if we look here, Alice's key is version 5, and then we're going until we actually hit a log entry, which changes the value of Alice's key, and then the counter increases, and then we kind of keep going from there. So next slide. The way that you search that is the way that you look for a specific version of a key is that you can actually just do a pretty straightforward binary search where you start somewhere in the middle of the tree. You say, what's the most recent version of the key that exists at this specific point? You see if that's greater than or less than the version of the key that you're interested in. And then you kind of recurse from there. You go left if it's too high, you go right if it's too low. And eventually, you'll always converge on the exact log entry where the key that you're interested in changed to the version that you're interested in. Next slide. So given that that's sort of in the back of our head about how searching works, we can also talk about how monitoring works. So we said earlier, monitoring is the process of making sure that our keys didn't change when we don't expect them to. Because for key transparency, it's important to be able to efficiently make sure that things don't change unexpectedly. Like if I store my public key in a log, I want to be able to make sure that people don't change my public key without me knowing. So the way that monitoring works, or well, sort of the security of this comes from the fact that search paths change infrequently. So if I look up my key and I see the search path goes to where I expect it to go, that binary search path is actually always going to be the same until the log basically doubles and you get like a new root node for the search. And then again, the search path is never going to change again until the log doubles again. And that's also what makes it very efficient, as the efficiency comes from the fact that binary search paths are logarithmic. So the log might double 10 times. It might be 1,000 times bigger than it was the last time I checked in with this log. But what that corresponds to is only about like 10 extra steps in the binary search path that users might traverse going to this specific version of my key. And if you're going to monitor your key, all that you have to do is go to the log server and say, hey, can I see these 10 log entries, which are the new steps in the binary search for my key, and can I check that they're constructed correctly? So can I check that there's no greater version or no greater version of my key being advertised that I'm not aware of, or we're not saying that my key has a lower version than I think it should. And as long as all of those sort of extra new steps in the search path point people to go back to the parts of the tree I've already verified, then it's secure because the searches will keep converging to the same place they kind of always have. Next slide. Okay, I guess checking in quickly, do people feel like they understand this so far? Okay, so the basic,
Nope. You go, Jonathan.
Sorry, I've been asking in the chat and I'm not really sure I understand. How do you check that somebody didn't add Alice 1 and then add Alice 1 again? Is there like if let's say I go and say I want to update my key,
right?
And I insert Alice 1, is there a way for me to check? Because I can check that Alice 0 exists. Is there a way for me to check that Alice 1 doesn't currently exist and like someone hasn't just been messing with my key?
Well, okay, so if you search for Alice 1, either that key will exist in the root node or it won't. Well, hold on. I think what you're asking is how do I make sure there aren't two different log entries in the log with the same version of the key? Okay,
Yeah.
So the reason that doesn't work is it kind of comes naturally out of the way that the binary search works, where the binary search or any binary search is always going to go to the first, element in the array that you're searching, where the version is now 1, if that makes sense. So if you do a binary search, it's not going to like converge to a different place than it would otherwise.
But it could be in a different, like, let's say in the first tree, like if you've got the log tree, there's prefix tree has X. Oh, I see. Oh, okay. Yeah, sorry. I follow.
Yeah.
Makes sense.
It's Friday, Jonathan. It's Friday. Mm.
But like, I've read the Merkle squared paper, so I get it at a high level. I don't get how the binary search path stays constant unless it's like a variation on binary search, because I would assume like if there's like 10 items in the set and you start in the middle, you'll be at like the 5th indexed element. But if it becomes 11 items in the set and you do another binary search, you're going to like start at a different halfway point.
Mm-hmm.
So is there something that like that seems like it would lead to not the same binary search path each time, is like in a naive binary search, but is it like in what way does it stay stable until there's like a doubling of the cardinality of the set? Okay.
I don't know that I call it prefix search, but you're right that we do choose the steps of the binary search in a specific way to make sure that it's as stable as possible. So the first node that we always start at with the search is the greatest power of 2 less than the tree size. And so if the first node in your search is always the greatest power of 2 less than the tree size, there's not going to be a new greatest power of 2 less than the tree size until the doubles. Yeah, yeah. Okay, so to describe it more explicitly, the algorithm for searching the tree is step 1, you do a binary search for the specific key inversion pair that you're interested in. For each log entry that you end up looking at in your binary search path, you have to look in the prefix tree at that specific log entry to find the greatest version of the key that exists at that point in time. And then you have to use that version to determine which log entry to inspect next. So essentially whether you want to go left or right in your search. And then eventually you get to you will get to the final log entry, and then that log entry will have the commitment that changes the key to whatever value you're interested in. But to kind of unpack a little bit deeper on step A, where we look in the prefix tree to find the greatest version, that's actually a little bit more difficult than it initially seems, because the prefix tree just contains a big set of key version pairs. It doesn't, explicitly tell you what the greatest version is. So you have to find that. Next slide. And the way that you find that is something that in the draft is called the binary ladder, which is actually a really terrible name, and I don't know a better name for it. But so to find the most recent version of a specific key from a prefix tree, essentially what you do is you check larger and larger powers of 2 until you get to the first power of 2 that doesn't exist. And then once you establish kind of this upper bound on what the most recent version can be, then you just do a binary search between that to find what the actual most recent version is. And yeah, so it's essentially just binary search again, recursively. There was an earlier version of this document that just had the prefix tree sort of directly tell you what the most recent version of a key is. But the consequence of that was that we would end up changing the tree differently based on whether we were inserting a new key into the log or updating an existing key. Because if you were updating an existing key, you would just change a value in the prefix tree. And if you were inserting a new key, you would insert a completely new value. And people didn't like that because it had, kind of privacy implications. Next slide. Okay, so the final algorithm for searching this tree is you do your binary search for each log entry in the binary search path that you're interested in looking at. You look in the prefix tree to find the greatest version of the key that it contains, which is secretly, under the hood, just another binary search. And then you use that to determine the next log entry. You recurse left to right until you get to your final log entry, and then you open the commitment, and you're done. Pretty straightforward. right? Next slide. Okay, so to kind of recap, the security guarantees that we're interested in here is that users can search for and monitor keys and have confidence that everybody that searches for the same key as them sees the same value as them. And also if they monitor a key, that key is never actually going to change without them knowing and being able to see it as well. And then the privacy guarantee that we're interested in is, to an outsider, how do we make sure that every change looks like just one new entry to the log tree and one new entry to the prefix tree? So we can never really tell deeply how the contents, the actual like data stored in the log is changing. We can't tell if new keys are being added. We can't tell if new keys are being updated. You could also like add a bunch of fake data just to kind of pad how busy your service looks. And then efficiency, every client-side algorithm is roughly logarithmic. Some algorithms are actually like logarithm squared, but that's kind of close as well. Yeah, so that's all I have. Any more questions? Okay, okay.
Yes, you're good.
Thanks, Brendan. Yaron, we do have a question actually, Brendan.
You're on, Chef, and apologies, this is kind of a higher level question, and just let me know if it's out of scope, but let me ask anyway. So for transparency, you want to ensure that the server that's responsible for this complicated data structure is not cheating and not giving different answers to different people. Is that in some way part of the protocol? I mean, for blockchains, there's a whole economic incentive thing that takes care of that. What do you do here?
So there's kind of a two-part answer to that. The first part is that because all of the contents of the log is stored in a log tree, that log tree has a root hash, and users intentionally hold on to that root hash. And whenever they send new queries to the log, rather than just kind of throw away their old root hash, they actually get a consistency proof to prove that whatever new version of the log new queries are being answered against is an extension of the previous versions of the log that they saw. So users guarantee that anything they were ever seeing is never deleted. Okay, so that's part one, is users ensure that anything they're shown is never deleted from the log. And then the part two of the answer is that users can either gossip with other users, or they can either poll the transparency log sort of over an anonymous channel to see that the transparency log is showing them the same version of the log over the anonymous channel that it does when they're asking it authenticated queries. Does that make sense?
Yeah, yes, it does. Does the protocol specify what's the minimum work I as a user should do if I care about a tiny amount of state on this data structure?
So it's not something that we can really specify in the protocol, I think, but what we do specify is the way that you can interact with the transparency service anonymously. Or I guess what I'm saying is, yes, it is part of the protocol. Either checking in over the anonymous channel or sort of exporting a code that you can compare with other users. Those are both part of the protocol, yes.
Thank you.
So do you want reviews?
Reviews would be wonderful, yeah.
So I linked your individual draft to the data tracker page for KeyTrans, so it's easier to find.
Amazing, thank you.
No problem. And I stayed away from the yellow button that's closed the working group.
Thank you so much.
It's
I
yellow.
think we can do Isha's presentation now, and then have a broader discussion maybe about the protocol draft, and see if what folks think about it, and see if we're headed in the right direction. And I guess to Brendan's point, if folks understand it. But yeah, maybe let's do Isha's presentation right now. Then let me pass you the slide control. There we go.
Yeah. Can you hear me okay?
Yes.
Yes.
Okay, great. Yeah, thanks, Shivan. And thanks, Brendan, for the presentation. So I'm going to talk about two different modes of key transparency, which was in the original, the architecture draft. And my proposal here is to sort of show how to tweak the proposal that is currently in the draft to see how to support both of these modes. So it's actually going to be pretty similar to the design that Brendan presented, but I'll go over it slowly to give a high-level overview. And um, the the motivation for this is I think some of the current deployments of key transparency at least is in a different mode than what is being presented in the protocol draft right now, which is called the client monitoring mode. So I think it might be nice to support both modes in the standardized protocol so that we can cover all the bases. So to give a brief recap, this is all mostly taken from the architecture draft. So key transparency in that architecture draft talks about three different modes in which we can build a key transparency system. So one is a third-party auditor mode. There is a third-party monitoring mode, which requires, to my understanding, a lot of data being outsourced, which may not be very suitable for privacy. So I'm not going to talk about that. So the two modes I'm going to talk about are third-party auditor mode and the client monitoring mode. And the differences between these two modes are in the first mode, it requires to have a third party auditor who the transparency log can delegate some work to. They don't have to be trusted for privacy, but they are a non colluding third party. Versus client monitoring mode, the mode that Brendan presented is where the clients do all the work. There is no reliance on an external third party to do any extra work. In the auditor mode, since the auditor does a bunch of the work, the users can run more efficiently. And in the client monitoring mode, the users usually have to do more work. And from the architecture draft, what it says is it's ideally suited for use cases where the users are looking up a small number of keys repeatedly. And finally, I think one of the most important distinguishing factors for me is the client's persistent state. And this is pretty important between these two different modes. So in the first mode, in the third-party auditing mode, the clients do not need to have any persistent state. And what that means is the client software do not need to remember any cryptographic signing keys or any other cryptographic state between its queries for the security of the system to hold. Versus in the client monitoring mode, they do need to remember that. And the reason the third party, while finding an auditor is often hard, the reason I think it is nice is because in some cases, the clients are light devices or they are not capable of remembering states, or you could lose all your devices, ending up losing all your state. So that I think, in my opinion, is one of the big distinguishing factors. And from my knowledge, the current deployments, both WhatsApp and Proton, are built in the third-party auditing mode, and I do not know of any implementation that's out there, any deployment that's out there in the client monitoring mode. If there are, I'd be happy to know more about that. So that was to recap on the different modes. Any question on that so far? Oh, there are, yes.
Great, Felix.
Yeah, hi, Esha. I was wondering about your claim that clients do not need persistent state. I argued to myself a bit about it, but just being naive, doesn't the client need to remember their key history to check that the server did not make any bad updates?
Okay, good. Yeah, thanks for bringing this up. So I am distinguishing between the client state and the user state. And by that, I mean the state that the client software, your app needs to remember versus what as a human user I can remember. And if you can remember absolutely nothing at all, I think some of this might be unachievable. So when I said clients do not need to remember, I really mean the software do not need to carry over any state. But we do expect the users will roughly remember when they did their updates, to the extent that if there was a malicious update, they'll be able to tell that, oh, that was not me. I was not online. I didn't do that update.
Okay, but I think this is something you could automate if you would assume client state, right?
With client state, you can do a lot, and I think client monitoring the proposals, including the one I'm going to propose right now, assumes client state. But think the key transparency will will be the most beneficial if it can support stateless clients, because the real case is like if you lose everything, all your devices, even then, if you can detect something is wrong, that it will be very nice. But yes, if you assume client state, you can do a lot more and
Okay, thanks.
efficiently, definitely.
Ben Schwartz, Meta, but I don't work on anything related to chat or key transparency. Don't the clients need persistent state to remember their own private key in order to be able to sign and decrypt messages?
So the claim here is if they lost their key and they reinstalled the app, so they got a new key, right? So in between, if the server tried to distribute a fake key on their behalf, they should still be able to detect it. So does that
Okay,
make sense?
okay, but if the client lost all its, if we're assuming that the client lost all its state, then the client doesn't have persistent state. But if the client and I regardless, you know, by assumption, but otherwise, I think the client always has persistent state. It at least has to have a trusted.
Yeah, of course, of course. For some time, if it's like a memoryless client and every time it's losing state, that's not much good. But what I'm trying to say is, even if it loses state, sometimes like you lose all your devices, you reinstall the app, and when you were offline, a fake key was distributed, you should be able to detect. Like this mode, the third-party auditing mode lets you still detect it. That's what I'm saying. So and the security is not compromised. So even in that world, you get security versus in the client monitoring mode, you don't get security if that is the case.
Okay, that's interesting. I have trouble understanding how that could be true, because if I lost all my state, then I am no more the owner of my account than anybody else in the world is the owner of that account.
Absolutely. And that is why the best you can get here is detectability. Like if you assume you have multiple devices and you can sign one with another, you get something stronger and you never lose your devices. But even the absolute worst case, you lost all your devices, this is the bare minimum security you get, which is detectability. So in the sense that you cannot publicly prove that there was a key change on your account, you did it and not the server. Or the server did it and not you. If you lost all your state, you cannot prove it to others, but you can detect that such a thing happened.
Watson Lad, Akamai. I understand why we're trying to have this detectability. I do question its real world relevance, because if we have a case where the device state is lost, we're relying on the user understanding when the key should have been updated in their human memory and remembering that their device was lost before or after that. I don't think that's terribly realistic.
Yeah, I mean, this is an assumption, of course, but do you think like assuming that the clients always have state is realistic? I'm not sure.
I think talking about what happens when you lose the device, we need to be clear about what we're assuming the information actually is. It's not going to be there was a change that I unequivocally know wasn't authorized.
Yes, yes. Yeah, we can be more clear about that, but that's what I meant. Like you can detect, and like I said, the user, there's an assumption that the user roughly remembers when they change their key so that they can at least detect if something looks suspicious. But it is an interesting question. If you don't have it, whether you can get anything out of key transparency. Unfortunately, I don't think the answer is very much. I thought about it some, but
Dennis Jackson, Mozilla. So I think that this is obviously an important discussion on some level, but I think we've kind of started at the wrong level. Like these are the technical distinctions between these two, but in terms of the actual usability, there's much more fine-grained notions of state that we do care about. So, you know, the most fine-grained, we've got my app is open up and it's crashed and it's gone and it's lost some of its non-persistent state. We've got the medium of like, I've got a backup somewhere that I can restore to from a day ago or a week ago or a month ago. And we've got the total loss. And I think you really have to talk about the actual use case for a real user, whether they have like a backup or not, whether it's a fresh phone or not. Now, there is still some like notion of identity, even if you lose all your state, based on like your phone number. or whatever that you can look up into this tree. So it's not the case that like your identity is completely gone. It's just that the private part of that identity is necessarily.
That's true. That's true.
So like, I think this is a really interesting question, but like, there's so much nuance here to unpack that I think it's tricky to do it at this level with this kind of very broad overview.
Yeah, thanks, Dennis. That's a great point. And yeah, totally agree.
Jonathan Hoyland, Cloudflare. I'm just struggling to think about a use case. And is the idea that it's something like I was arrested, all my devices were taken off me in an unlocked state, and then when I finally get out, I can see, oh, somebody like issued new keys. Is like, yeah. What's a real use case for this?
A real use case is I have only one phone and I lost it, and there was a malicious account. Like, I mean, that's also a very simpler, but real use
How would
case.
there be a malicious, like if my phone was lost as opposed to
And
stolen?
somebody distributed a key on my behalf, right? So, and that will be a use case. That will be, I mean, there are a lot of realistic use cases, and I don't necessarily want to branch off into that discussion because that's a different and a much bigger discussion. But I think it is a realistic use case, right? That you lost your device or your device was compromised. Somebody have added another device on your account and distributed a key. And when you reinstall the app, because like Dennis said, you haven't lost your identity in the system. So you still want to be able to detect that such a thing happened.
Okay, thank you.
All right, so looks like no other questions. So should I proceed?
Yeah, please do. Yeah.
All right, so this is a very high level overview of the asymptotic cost that the present, like the proposal I'm going to present will have. So the asymptotic costs are like this. So in the auditor mode, the cost of auditing is T log n, where we are allowing T updates per epoch, at most T updates per epoch, and say the size of the entire directory is big N. In client monitoring, obviously there is no third party, so there is no third party auditing cost. The search and the monitoring cost here. So search means I'm looking up somebody else's key, and monitoring is I'm monitoring my own key history. And these two costs totally unoptimized. Like if you store some of the states, you can do it like way better. But here the worst case cost is if you have V version numbers, like if you have V keys on your account, then this cost is V login. And versus in the client monitoring proposal, based on the same data structure combined to construction, in the client monitoring case, the cost is there's a multiplicative log E factor. And let me go into a little bit depth of what E here means. So in this world, we are assuming that the clients are not always online. So they might be offline for certain epochs. And if so, let's say they come online between two epochs and the length of their offline period was E. So then this cost is V log n times log of E. So log of the interval when they were offline. And the clients in the first case do not have persistent state. We had a lot of discussion about that, but here I meant like really, you don't have to carry any state between these two queries to make sure that that the security holds. Versus in the client monitoring case, that is you need that persistent state. Okay. Okay, so here is a quick cost analysis difference between the current protocol proposal and what I'm going to propose, and we are calling it weakly consistent optics because optics is a proposal in the third-party auditor mode, and in the paper I linked that shows how to do it in the client monitoring mode. So there is a cost difference, and again, like I'm not making any claim of which is better or worse. I'm just showing that there is a cost difference here. But again, I think the main difference in my mind is that persistent state requirement, which if you look at the third-party auditing case in the current proposal, the IETF protocol, the KEYTRANS protocol, and the optics, these are the differences. So the audit cost, I would say, are actually very similar. So in our case, is T log n. And in the protocol draft is log n because only one update is allowed per epoch. Versus here we are allowing in this proposal T updates for epoch and the cost is T log n. The cost of search and monitor differs like this. So in the case of monitoring, the search of monitoring and searching in the protocol draft is log v log squared n versus it's v log n in our model. Because to the best of my understanding, in the protocol, you could add an auditor, but it is not obvious how you will change the search and the monitor algorithm to take advantage of the auditing. And that's why that draft will still require the clients to have persistent state versus the draft I'm going to propose won't. Those are the high level differences. So any question on that? Okay. Oh, there is a
So
question. Yes,
actually,
Philip.
yeah. Can you go back a slide? I just realized. So you
Yes.
say, I mean, there is a fundamental difference in how third-party auditing and client auditing usually works in the right, because the third-party auditor, they play like a global police. They look at everything and whether the log as a whole behaves correctly, right?
Yes, I mean with privacy, but yes.
Yeah. So you have this factor V now. For client-side monitoring, V makes perfect sense because the client has like V versions. But for V in the third-party auditing model, it's not quite clear to me what V here means. Is that the average version of any user? Is that
No,
do
let
they
me
need to
clarify.
perform this per user?
No. So V is not in the third party auditing mode. The auditor cost doesn't have V. So that is T login. So T means the total number of updates that happened between two epochs. And we allow batch updates, which I think is
Yeah,
different from the
sorry. Yes,
current proposal.
I got your rows wrong. Sorry. Thanks.
Okay, no problem. Yes, Brendan.
Hi, I am so sorry to rehash this conversation, so I'm going to make it a clarifying question instead. When you say clients don't need persistent state, what persistent state specifically are you talking about? Are you saying they don't need to hold on to a tree head? Are you saying that they don't need a signature key? What do you mean
They do
there?
not need a signature key. They do not need to cache the previous states of the keys to make sure that that security still holds. They do not need to maintain any of the states. Yeah, more questions.
Hi, Watson again.
Hi.
I'm a little confused by why the search costs are different in the two. Isn't it a very similar data structure that the client is directly looking things up in both sides?
I will talk about the data structure in a bit. So the prefix tree, at a high level, the data structures are very similar, but there are some slight differences. And and the search and the monitor algorithms are also different, even though the server's data structure is the same.
Okay, and a quick follow-up to Brendan's clarifying questions. You used the term signing keys. By that, you mean signing keys that a client would use to sign their message, or do you mean the public keys are used to verify the signatures of the log or similar?
No, not of the logs, the client's personal state. Yeah, like the
Great,
private
thanks.
state of the client. Yeah. Yes. All right. Moving on. Yeah, so at a high level, the data structure looks very similar. And as you can see, this slide also looks very similar to what Brendan presented. So the idea is there is an append only, maybe there's a slight difference in that there's an append only prefix tree for every epoch. And these roots of these prefix trees are the leaves of a log tree. So the upper triangle for me is a log tree, which I think, Brendan, you used gray boxes to indicate. There is one difference though. So first is between the two roots of the prefix trees, we are allowing a batch of updates instead of one. And the roots of this the leaves of the log trees, which are the roots of the prefix trees, they contain the roots of the prefix trees. And the prefix tree structure, like in Brendan's proposal, I think it contained, Brendan and Felix, the root and a commitment, versus here I'm saying it only contains the roots of the prefix tree, and the prefix tree underneath collects T updates between two epochs. And next I'm going to show you like how, and the prefix tree structure is the same, but the leaves look a little different. The construction look a little different. So the next slide was going to clarify. But this is the high level combined structure Is it sort of clear? Going to assume that's a yes. I'm going to move on. Okay, so the prefix tree construction is again pretty similar to what Brendan showed, with two significant differences. So the first difference is in the leaves, there is the commitment to the value itself, like we call it like the encryption key, say the public key, is hashed at the leaf itself instead of with the root. Um, and along with that, we also add the epoch number t at which it is added in the clear and then hash it in the prefix tree. So the leaves of the prefix tree look a little different. Note that the leaves positions are computed exactly like in the proposal using VRF, which was first introduced in Seamless. So the label is basically the username concatenated with the version number, which are the input to the VRF. And those bits are used to compute the tree, and compute the position in the tree. And then the tree is computed the same way that Brendan presented by hashing them upward.
Isha, I
Yeah.
think just one clarifying question from Jonathan in the chat. If the client doesn't have any state, how do you know that you're talking to the right endpoint?
No, I think well, Dennis's point was right here. It's a nuanced conversation what exactly state means. But what I mean here is that the client does not need to remember from the previous query and this query what, like, let's say I looked up Alice's key before. So does my key state need to remember Alice's key version so that the next time I do an audit, I can is it required for the security to hold that I need to remember Alice's state exactly so that if some misbehavior happened on the account, I will detect it, versus I start a fresh account and I'm doing a search on Alice's key. Is that enough to detect that some misbehavior happened? I think that's the difference.
Go ahead, John.
Jonathan Hoyden, Cloudflare. So you are still keeping the tree head or the root, because if you're not keeping the root, otherwise the key transparency server can just be like, hey, I invented this whole entire new tree and I actually own every single key and it's completely fake. And I can't tell because I don't remember anything.
Yeah, I think Felix responded to that in the chat and is right. You can assume that's hard coded, like the certificate of where you look up the
The
trees.
tree head is hard coded?
No, the
No,
certificate, like where you, sorry, go ahead. Somebody's
yeah, but if I may jump in, Jonathan, I think you can anyways assume that you agree on the root hash with your peers, right? Be it via gossiping, be it via querying it
Yeah.
through anonymous monitoring. You don't need the history still. You just need to make sure you have the same as your peers. Then the server cannot replace the word. But you need to do this in client-side auditing anyways.
So we're saying that as long as I can always trust my peers, because remember, if I've got no state and I want to talk to my peers and I'm going to the transparency server to get the keys and the transparency server is just making up keys, the transparency server can pretend to be all my peers and give me the tree head.
What I wanted to say is there, of course, I mean, you point to a right problem, but I think it's orthogonal to this discussion, right? You need a way to ensure with your peers that you're using the same root hash in any sort of monitoring. And yeah, I don't think Esha talks about that here.
No, yeah, that's right. Yeah, Dennis, please.
Yeah, just to sort of plus one what Felix said. I'm going to wait for Jonathan to finish talking. So just to clarify, right? If you end up locked in a box and you never talk to anybody else and all your communication goes through your phone and the attacker controls your phone at some point, it's over. However, for many people, they get new phones from time to time. And like they have the ability to move between networks. And in a realistic model, at some point, you talk to somebody that's not the attacker. And then you're like, oh, damn. Yeah.
Okay, thanks. Okay. All right. So I think the construction was understandable, hopefully. So in this construction, now we will see how to use it in both the audit mode and the client monitoring mode. So if there is an auditor, then this is how the algorithms will look like. The audit algorithms will check the append only completeness of the prefix tree, which means it will check that the old trees are the old tree is a subset of the new tree. And it will also check that the new leaves have the correct epoch number, because the epoch numbers are exposed in our tree. There was a question about why the complexity looks different, and this is because the search and the monitoring algorithms are slightly different. So because in this world there is an auditor who's checking that no entry from this prefix tree ever got deleted, we can do something lighter weight on the clients. So when somebody searches or monitors, we don't actually have to find the highest version number in the tree. Instead, we will let the server serve you the latest version number in the tree. But what we would want, let's say like Bob's current version is V3. Bob has 3 key versions. So the server will serve 3 membership proofs in the latest prefix tree, along with the non-membership proof of the 4th version. So it proves that the version 1, 2, and 3 exists in the tree and version 4 doesn't. And the reason we can do this is because the auditors are making sure nothing ever got deleted. So if the server ever tried to make anything, insert anything, it will never be able to delete it. So this lightweight monitoring and search algorithm will work. I mean, there's a formal proof in the paper in optics, but to give a high level intuition, this is the search and monitoring algorithm are different from the current proposal, and this is in the auditing mode. Okay, there are some questions. Is there any question for me? Sorry, it was.
Go ahead, Jan.
Yaron Sheffer, back to the previous question and to Dennis's answer. So if I'm in a box and now I'm out of the box and I'm talking to Jonathan and I totally trust him, but I'm talking to him I'm talking to him through the centralized system, because all of these are centralized organizations, and the main threat model is the centralized organization trying to man in the middle me, because they don't like me. So I still fail to understand how I can recover from that.
So I do agree with some of that for sure. Like, I think, in a world where we had like really decentralized communication and it was all federated and this kind of stuff, the case is much stronger. I think in a world where things are more centralized, it gets harder and harder. I agree. But I think in practice, we do have systems that, while still centralized, approach that. Like, I think Signal today can make a credible claim to not know who is trying to send a message and to who they're sending it to. So for that specific use case, I think there's a very strong argument for systems like this. I agree that for like Gmail, maybe doesn't need key transparency, but it's got its own problems.
And also adding to that, Yaron, I think I hope I really build on anonymous routing to agree on, not to agree on, but to get the signed tree heads, like kind of just the short version of the tree. Because if you use anonymous routing, the chance that the server can lie to you successfully is much lower. And it will be incredibly low. And these queries can be very small. You don't need to do them a lot. And you really don't need any state to have faith in that the tree head you got via anonymous routing is the same that everyone else got.
Go ahead, Thibault.
Hi. Yep. Hi, Thibault Cloudflare. Maybe one thing I think that could help here is my understanding of key transparency is it does not try to provide integrity, even though it like approaches it. It provides consistency. And so in the case of even like centralized messaging systems, like I know we could take Gmail or etc. If they're already like rolling out key transparency, it means like they actually would like to commit to like some consistency overall, and they probably won't roll out only key transparency as like a security mechanism. Like QR code might still be around. There might be like other ways to go set your public key and to ensure that like this route that you get is actually legit, and so that like you can communicate it to your other peers. So I definitely agree that like like a central entity could like work in like a split view and totally isolate you, but I'm not sure if it's a realistic model, and like that's how key transparency is going to be deployed in the end.
All right. All right, thanks. So moving on. So this is going to be, I'm not going to go into the algorithm here, but this is to show that using this very same combined tree structure, in the absence of an auditor, we will still be able to detect a misbehavior. For example, a server gives a fake key for Alice to Bob and some epoch when Alice was offline in this picture. So these commitments are your roots of prefix trees. And in this case, we would like an Alice and Bob during the search and monitor to do some additional checks to be able to still detect such a misbehavior in the absence of an auditor. And of course, there is an inefficient approach of solving it, which is Alice could, when she comes back online, she could check in every missed epoch that her key was maintained correctly or it did not change. Connix roughly takes this approach, but we would want to do better. We actually do not want to check all these missed epochs, and that is where we had this. Obviously, it's not trivial because you will need to find some sort of intersection where Alice and Bob can still check logarithmic in the length of the epoch, the length of the interval they were offline, and still detect that this happened. I'm not going to go into the algorithmic detail here, but in this paper, well, the algorithm was first proposed in this paper called Versa. We simplified the algorithm a bit to show how there's a deterministic algorithm which you can use to pick some of the epochs from the missed interval in a way that if Alice checks those epochs, her key consistency for those epochs, and Bob also checks Alice's key consistency for those epochs, if there was such a misbehavior, it will be detectable. I did not want to go into the detail here because I don't think that's of interest. We can do it in a future version if it's of interest, or look at the paper or discuss offline. But the point here that I'm trying to make is the very same data structure can support both of these modes simultaneously. And with that, I'll summarize just to say that here is a candidate construction. There's plenty of room for algorithmic optimization and storage optimization here for this client monitoring mode. But the point is, yeah, it makes client more efficient and with a very controversial but no persistent state in the way I originally meant it. And I'd be interested to see if this is something of interest, if you think it will be interesting to support both modes, specifically because some of these larger deployments are actually in the third-party auditor mode instead of contact monitoring. So I'm interested to see what the group thinks in terms of expanding the scope of the protocol to support both modes. And thank you.
Thanks, Isha. Go ahead, Felix.
Yeah, thanks for the presentation, Isha. I was wondering, to what extent does the current draft not support third-party monitoring? Because you could have third-party monitors that just monitor the log tree for its append-only property, right? That is something that third parties can do.
Yes,
so what
exactly.
do you think exactly is missing?
Yeah, so I will go into that. I had a slide on that, I think. Did I? Yeah, I did have a slide on that. So I think, yes, that you can definitely do, but I think it doesn't take advantage of the fact that there is a third-party monitor. Because if you take advantage of that, the clients can do a lot less work, and that's why the efficiency looks different. And also the client do not need to keep state, which I understand is like, there's a lot of nuance in it, but in the sense I originally meant that it doesn't have to remember what was Alice's previous key state to do this. And I think in the current proposal, it's not supported to the best of my understanding.
So clearly, because there are different tree constructions, we have different complexities, right?
The tree constructions are not that different, right? So if we don't allow for batch updates in our model, it's kind of similar, except that we have like the leaves of the prefix trees look a little different. But I think the algorithms are really taking advantage of the fact that there is a third-party monitor in one case, and in the other case it's not. Although like my monitoring algorithm is slightly different from yours, the one we have in the paper, but that's okay. Like it could have different, slightly different trade-offs. I don't think that's the moot point. I think the moot point is if there is a third-party monitor, that is not taken advantage of.
So I fail to see the point where this is not taken advantage of, because on your last slide, you also showed how a client Alice needs to go over the history in like logarithmically many steps. And this is exactly what's happening with the binary ladder search that Brendan explained, right?
Yeah, absolutely. Okay, sorry.
So
Sorry for the
I would be
confusion.
curious to really
Mhm.
understand, yeah, if you could really say like in our draft, in your draft, you do this, which would be unnecessary if there were a third-party auditor. I would really appreciate that.
Absolutely. Yeah, sorry if this was not clear. So this part, this algorithm, which is the client monitoring algorithm, is similar to yours, because the Alice has to keep state and check some consistency. And this is exactly the thing that clients won't have to do if there is a third party monitor. So if there is a third party monitor, the only thing that they need to check is this checks that version, whatever version number they're getting back from the server, up to that version exists in the tree and the next one doesn't. That's all they have to check. They don't have to keep any state and remember what was Alice's key state before, is it consistent with that. So this is the third party auditing mode that I'm proposing. Was the other, and the slide that you are referring to is the client monitoring mode of the same data structure, which is similar to your protocol. But these are exactly the checks of checkpointing that the clients won't have to do if there's an auditor.
Okay, just to quickly double check, then I'll open the floor for others. But so you're saying key queries could be made more efficient?
Exactly, and also you don't have to remember the state of Alice's key from your
Yeah,
previous
okay,
query.
okay, okay,
Yes.
great, thanks.
Yeah, thanks.
Watson Lad Akamai, I'm sort of confused by what the difference in the data structures is. I think what it is your pair epoch data structure is indexed by a combination of Alice and the epoch on her keys. And so you're trading off in the lookups a binary search, which adds that log n squared factor and adds a log v. You have to go do v queries. I have to go as a client query for a whole bunch of possible epochs and then do lookups for each one, figure out what the latest one is. Do I sort of have that right?
I'm not sure it's that exactly, because it's still indexed by Alice and the version number. So, okay, just to be clear, so you're talking about the client monitoring mode, right? Not the auditing
I'm
mode.
asking about the slide with the search costs on it.
There are two slides. So there's a
Yeah,
slide.
the slide with the comparison.
Okay, let me go to that. This one?
Yes, that one.
Okay.
And I think, and maybe it's not important if I'm wrong, but my thought was, okay, the reason the search in WC Optics, which I understand is sort of the presentation here, is you look up V epochs and do log n work for each of them to see whether Alice has a key in that epoch as Bob.
Yes, it's not V epoch. Yeah, but it could be in the latest tree because it's an append only tree. But yes, roughly.
Yeah, you do it, but you have to do a lookup for each one, roughly. Yeah. Whereas in the Macmillan protocol, it's you do log v work, figuring out what epoch it is, and each step of figuring out what epoch it is. I'm not sure why there's a log squared n.
It's because you have to do search in both the prefix tree and the log tree to find the actual commitment. But
Okay.
I think roughly it's roughly.
Yeah,
I
I mean
right.
it's a log. It seems to me that this is almost orthogonal to the third party auditing in that the third party auditing isn't what's leading to the speed ups here. It's just what you've decided to store.
No, I would disagree with that, because there is a third party auditor who checks that no entry ever gets deleted. You can do this, because otherwise you will have to do more work, which is exactly what we do in the client monitoring mode, where you actually have to go back and check in certain epochs that something is maintained correctly. So it's slightly you are taking
Because
advantage of the fact.
because the append only property of the prefix trees is only that's where the extra log n work is coming from then.
Yeah.
Is from having to check the append only property on lookups. Thank you.
Yeah. Thank you. Yeah.
Hi, so I wanted to say that there are two deployment modes, third-party auditing and contact monitoring. In both constructions, either optics or the draft protocol, when you're in contact monitoring, you have to do a lot more work. You have to do the contact monitoring work. When you're in third-party auditing, you don't have to do that in either protocol. So the draft protocol is not going to be as efficient as optics in third-party auditing mode, and optics is not going to be as efficient as the draft protocol in contact monitoring mode. But when you frame it that way, it becomes a very easy like numbers question, like this mode has this many bytes per query, and I think it's probably simpler when you frame it that way.
I'm not sure. So what is the question? Sorry.
It was just a comment that in both protocols, we can be more efficient when we're in third-party auditing mode than when we're in client monitoring mode.
Yeah, yes, yeah, absolutely. I think the thing is in the current protocol, and correct me if I'm wrong, but in the current your protocol, I don't know how your auditor takes advantage of that having an auditor. I'm convinced that it can be extended to that, but I don't think it exists right now. So what I'm proposing here is a candidate construction that supports both these modes. And I'm opening up the floor to the discussion whether it is worth doing in the sense of whether it's worth extending the protocol to support both modes so that it can cover the current deployments and also is more generic.
Yeah, I mean, I guess given that it is an individual draft at this point, my question was going to be to the authors of the draft, specifically to see if there was interest and like what the thoughts were around expanding the draft to have both modes, with the caveat that at some point the draft has to be adopted. So also interested in what the group thinks the author should do. We have about 18 minutes. Not sure if we need all that time, but I would love comments by folks on the topic of whether we think the draft that Brendan and Felix have right now, if that's headed in the right direction, and if separately, if Isha's dual mode expansion is necessary for the draft to be adopted.
Hi, this is Hannes. Listening to the presentation, it seems to be that both sort of proposals are very close to each other, and I was wondering what type of runtime we actually talk about in absolute numbers. So, like, if I have in the third-party auditing case, like I want to check the consistency. Like, what would that actually mean, like in practical purposes? Like, how large is N, and how large, how costly is one operation? Like, how often do these whole operations have to be performed, and so on? These type of questions.
Yeah, so there are a couple of papers, a series of papers I can link you to, because it really depends on what is the size of your user base, how often the key changes happen. But the operations are pretty cheap because it's like a one VRF verification and it's a couple of hashes, maybe like 10, 20 hashes.
Okay. Yeah, if you have some papers, that would really be helpful. Thanks.
Yeah, definitely.
Take a look at them. Thank you.
Are the others aware of any deployments of these protocols? Or I guess either.
Yes, so this the WhatsApp deployed Parakeet. With the paper Parakeet is a version of that is deployed in WhatsApp. Proton has a white paper out. The construction is slightly different, but it's also in the auditor mode. They have a white paper explaining that their deployment.
But to my knowledge, none of the designs discussed today are deployed. I mean, Escher, you need to speak for yours, but
No, the tree is deployed, right? So the tree structure is very similar. Well, not maybe exactly, but it's pretty similar to what WhatsApp deploys. It's in the Parakeet paper.
okay, yeah, then I've got that wrong. Thanks.
So I guess kind of putting you on the spot, Brendan and Felix, do you have thoughts on whether the draft should be expanded to include Escher's proposal?
So I must be honest and maybe humble. Escher, I've read your paper a couple of times before, and I thought that it is very close to the design that Brendan came up with and that I helped editing in the protocol description. And I fail to see the critical differences that would, yeah, like the breaking point where this one change. I mean, you propose a different design, and your design has many good properties, and I see that. And Brendan proposes a design, and I think his design has many good properties, and I see them. And they seem so close that I personally don't understand where the exact difference lie, other than a log factor. Yeah,
No,
but
it's not a question about in my mind, it's not a question about the efficiency. It's really a question about you could expand your protocol to support the auditing mode, which right now the protocol doesn't have. And it's a good thing the data structures are close to each other. I'm only saying that it doesn't support the auditor mode right now, and it will be, I think, nice to support that.
But as Brendan said, we can just add a third-party auditing mode. I think I need to think this through thoroughly. I don't want to make any calls here, but I think we can just add a third-party auditing mode, and
Yeah, and you
don't
have to
need to change the tree construction for that. Maybe Brendan, you're at the mic. Maybe you want to say something too.
Yeah, I just wanted to say that because the two proposals are so close, I think that the right.
Sorry,
I
the
can't
mic
hear
is
you.
going off.
Sorry. What?
He's going to the back.
Because the two protocols are so close, I think the right resolution here is to maybe decide this offline between this and next IETF.
Yeah, that sounds good to me. Prachi, my co-chair, and I can talk to, I guess, all three authors and see what to do next. If folks have comments and thoughts right now, we have time to do that. Otherwise, the mailing list is always open. I think that was, yeah, pretty productive. Does anyone have any other thoughts or comments before we wrap up? Deb, did you have anything else?
I do. I'm sorry. I forget I have a mic right here. I do not. I'm good. It's Friday.
Right. In that case,
just to remind myself.
thanks all, and see you on the mailing list.
Thank you very much. Thanks to Lee for taking notes.